Good afternoon. Today we are going to see a forward and reverse kinematics for a robot. So these are some practical applications where you can see the forward and inverse kinematics. So here you can see a manipulator. It is collecting some picking an object from there and placing it here. So doing these things require a lot of math. There's math behind it. So let us look one more example. The first case shows the picking up a mobile by a human hand. Because humans are very easily able to pick one object without much. There is a calculation because the calculations are happening on our neurons. So in order to pick, when we pick some objects, we with our eyes we can know that how far it is, and based on that we will pick one object. And if it didn't reach that distance, we know that little more distance need to be moved to pick that object. So these calculations are done by neurons in humans. While in the case of robots, you have to do the same thing with help of some math that you have to, but that we are going to study today. So it's not an easy task for robots. So before going with the forward and inverse kinematics, you need to know some basics. So what's in the robot manipulator? So this is the first thing. A robot manipulator is something that has a base. This is called the base of the robot. And you can see these are joints. Joints means with this joint it can move motions. So this is the first joint, like second joint. Here also the motion can be there. Motion means since this is a rotation joint and is rotating, so it can move like this. Similarly, here these all are rotation joints. So third joint, fourth joint. So these are joint 1, joint 2, joint 3 and joint 4. Okay, and there is some part that exists between two joints. So that is called the link. So this will be link 1, this will be link 2 and this will be link 3. And this part you see here, this is called the end effector. End effector means that is the thing that will do some action. For example, to pick some object, pick and place some object, then drilling, welding, those sort of things. So this is called end effector. E. So these are the main parts of a robot manipulator. Usually, robot manipulator, when we say it only includes the base, joints and things, we will avoid the end effector because end effector can be changed based on our requirement. If it is for welding, we will attach a different end effector here. If it is for picking something, we will attach a different end effector. So based on our needs, we are changing the end effector. So robot manipulator only include the base plus joints and links, except the end effector. Now let us see what is meant by a workspace for a robot. So workspace means space where the robot will operate. So this is one robot that is known as Cartesian robot. Why it is Cartesian means along the y, along x, y and z, the motions are linear. Means here you can see this thing is moving. So it can move along this direction. So x there is a motion, and here it can also move along this direction like this. So y there is a motion, that is also linear. This is linear, this is linear, and this thing also can move up and down. So that is a motion on this axis. So this is also linear. So it is LLL rotation, LLL motion. All are linear. So that's why it is called a Cartesian robot. And when you see the workspace of the Cartesian robot, okay, when it moves along x and y axis, what is the figure that you will get? X and y axis, what is the figure? X means it is moving like this, y is moving like this. So what is the figure that you will obtain? Rectangle or a square. If this thing also moves down, up and down, so totally what will you get? 3D. Cuboid. Yeah. It's a cuboid. So its workspace will be a cuboidal workspace. We can see. And next is a cylindrical robot. So cylindrical robot. Wait, you stop
Mechanical second year. There are only 3 mechanical second year. And after now.
Okay, next is cylindrical robot. So here you can see this is rotating around this axis. So it has a rotation. Then there is a linear motion. Then this also have a linear motion. So two rotations. One rotation and two linear. This is linear, and one is rotating. So that is a cylindrical robot. Seeing its workspace, when this thing move up and down, this thing also moving up and down, that will describe a rectangle. And when this is rotating, it will describe a cylinder, part of a cylinder, not fully cylinder. Okay. Then only this much area is in between this space is obtained by this some parts. Similarly, for a spherical robot, there all the things are rotation. One linear and both two are rotation. So this is rotation. There is rotation here. There is rotation here. Then here only one linear motion is here. Okay. So it is LR. So based on seeing that thing, there is a linear motion and rest two are rotation. So it will describe a part of a sphere. So this is basically the workspace of the robot. So this is the space where the robot can operate. That is called workspace of the robot. Now let us see what is the degrees of freedom. Before going to these figures, let me explain some simple figures. Consider a simple robot. Okay. So, as I said, this will be base. This is a manipulator. So, this is called the base. This will be joint. There are also rotations there. And so there are rotations here. There are also rotations there. And this will be the intersection. Okay. So let it be moving an angle theta 1. This joint will be moving. This is joint 1. This is joint 2. This joint will be moving an angle theta 2. That is the intersection. So degrees of freedom means the independent motion in which the robot can move. So it can move theta 1 in one orbital joint. There are also one orbital joint. So the degrees of freedom for that robot will be 2. So independent motion in which the robot can move. So this link can move theta 1, that can also move theta 2. So two motions. So 2 degrees of freedom. Okay, let us discuss the degrees of freedom for this. This is a scalar robot. So this is called the base. That will be fixed. Okay, so here is the first motion that is happening to the robot. That is along z axis. Here is another along z axis. Here, seeing this image, you can only see the screw will move up and down, but there is also one rotation to the screw also. So there are two motions are there. This rotation is also there. It will also move up and down. So here there is 2 reals are there. So 2 plus 3, 4. So it is 4 reals. So these 4 are 4 independent motions. Here it can rotate, here it can rotate, here it can rotate as well as move up and down. And this moving up and down, that joint is called prismatic joint. Okay. And the rotation zones are called revolute zones. And this is Puma robot. Here, this is the base, and here there is one rotation. In this axis there is one rotation, that is represented by this. Here also one rotation is there. Here also one rotation. So this part is called the end effector. So avoiding the end effector, this thing has 3 degrees of freedom, including the end effector. This end effector also has 3 degrees of freedom, like the wrist of our hand. It can move up, like left this, and all the 3 motions are there. 1, 2. Yeah. It's like a wrist. Till this point is our manipulator. We are including a manipulator. This arm is considered as an end effector. So that we are not including usually when we say robot manipulator. So including this, this has a 3 degrees of freedom, which has a roll, pitch, and yaw. You know what is roll? Pitch means this, roll means this, yaw means this. So this part is actually doing that, roll, pitch, and yaw. So because of that, it has 3 degrees of freedom. So total 3 plus 3 6. The human robot has a 6 degrees of freedom total. So now let us see representation of a point in space. So we all know that a point in space can be represented by, if P is a point, I cap plus B j cap plus C k cap. Right? This is vector representation of a point in space. So matrix representation of this point can be written as A, B, C. Okay? And this is another kind of representation where we use one more additional term called W. That W is called the scale factor. Scale factor of the. So if a point has a, if the same point has a scale factor 2 means that it will become 2A, 2B, 2C, and 2. So that will actually zoom the existing vector, doubling the magnitude like that, depending on the values of W. So in general, we write P is equal to the vector P will be equal to Px P by P is a W, and where the Ax can be written as capital Px divided by W, By can be written as Py divided by W. Similarly, C can be Cz can be written as Pz divided by W. So then you need to know what is meant by W is equal to 1. What is if the scale factor value is 1, which indicates the same vector itself, Px P by P is 1. So this is same as Ax A by A is 1, because multiplying by 1 20 is 1. So that means its magnitude remains the same. Then if W is equal to 0, what will be X? X will be infinity. By will be infinity, and Cz will be also infinity. What it represents? It represents a vector having an infinite magnitude with direction. Right? Because its magnitude goes to infinity, but only direction is there. So this will, when W is equal to 0, P will become Px, Py, Pz, and 0. So this will only represents the direction of the vector. We are not considering the magnitude. Even though infinity, but for our representation, we are considering that's the direction of the vector. That's it. So from here onwards, we are following this notation to represent a point in space with this Px, Py, Pz, and scale factor will be 1. If it asks no magnitude also. it's not magnitude one, it's scale. If a vector is 2ik plus 3jk plus 4kk, so when you're representing in the matrix form, it will be 2, 3, 4, 1.
Representing it as 0. When you take only the unit vector normalized to one side, that means the 3 points will be normalized.
You're saying magnitude 1.
When you are taking W to 0.
No, no. We can represent the same vector. W is 0 is represent the direction.
Isn't it represented using unit vector?
Unit vector. Yeah.
And that scale factor is used in the vector problem just to zone it.
Now, while dealing manipulator, there we will be considering frames. So there will be one fixed frame. So let that frame be x, y, and z. So this is a fixed frame. So that is being represented by x, y, z. So it can be called as f, x, y, z. And the second frame, that is a moving frame, means some motion happening to the frame. So that frame is called FNOA frame. FNOA frame. So NOA. So similar to the direction x, y, z, it will be NOA. Okay. So these are the first figure represents the there is a fixed frame and the rotation happened to the moving frame. Only the rotation, no translation. That means it is rotating with some angle with respect to the this frame, bigger frame. Okay, that you understood. And second figure represents the rotation as well as the translation. Means this smaller frame undergo some rotation with respect to the this bigger frame. That means fixed frame as well as a translation also. Translation of P also happens with respect to the this frame, front frame or fixed frame. Because this frame won't be changing because we will be considering this as a reference. There should be always the reference side for measuring something. So that will be only the moving frame. So these are the frame representation, and if this frame undergoes some particular rotation, let me talk about orientation first. Assume that this frame undergoes only the orientation. Okay. As you can see here, this is only undergoing rotation, not translation surface. I think hope you all know about direction cosines. Let me explain that. If a vector is there, x, y, z, I have some vector. It will be p. It is making an angle alpha, beta, gamma with respect to x, y, z axis. So cos alpha, cos beta, cos gamma. We can write the vectors like that, such that this will be called as L, this will be M, and this will be N. Such that L square plus M square will be equal to 1. So it's a unit vector. In other ways, we can write that direction cosines are, since I know what is P, so I can call P as A, B, J, C. It's A, B, J plus C, K. So I can write P as A divided by root of divided by its magnitude, root of A square plus B square plus C square. This will be L, that is cos alpha, and M will be cos beta, that will be B divided by root of A square plus B square plus C square, and N will be C divided by root of A square plus B square plus C square. So this is what direction cosines are. So when you are taking its magnitude, it will be unit vector. Similarly, you can see each axis, right? N, O, and A, right? Since these vectors are rotating, means the smaller frame, that is NOA frame is rotating. So in order to mention its orientation, we are considering the direction cosines of each axis with respect to the XY frame. Means let okay, assume that this is a new orientation of the NOA frame with respect to the XY frame. So I am considering some point on n-axis, and I can get the cos alpha, cos beta, and cos gamma, right? So that is actually nx n by ns. Similarly, n second O, I can consider some point, and I will get for it also cos alpha, cos beta, cos gamma. So again direction cosine, that is 1x over cos. Similarly for the other also again. So this actually what represents is that orientation of the display, smaller thing. Okay. Any doubts? By representing the direction coordinates of each axis with respect to the x-y-z axis, we will get the orientation. So that is represented by nx n by nz, ox over y, ax y by az. No area. I said about one fixed frame rate. That will be x, y, and z. The frame which is moving, I can call it as N O A. So that is we don't usually put same symbols. So this frame is called, since it is represented by x, y, z axis, so it is called fx, y, z and fy. Two different frames. This is what I said. This is actually the direction of x. Value will be so root of nx square plus ny square plus nz square will be equal to 1. So magnitude will be 1. Similarly for O also, A also will be 1. And then now I will go with this part. Okay. Assuming that our vector undergoes this thing, this NOA frame, smaller frame. This is the NOA frame, okay, NOA frame. NOA frame undergoes just a translation. Here you can see rotation also, but since this already translation happened with it, let it be P. So by deriving it into its component, I can say in along it will be Px, y will be Py, and z it will be Pz. So that is actually represented here. Its translation form. If it undergoes both rotation as well as translation, we can represent the whole instances. Nx, ny, nz, y, y, z, ax, y, z, px, py, pz. And now the last part. Last part means earlier I said to represent a point in a space, we will usually follow px, py, pz, and w. Right? This is the representation for representing a vector in space. So, what this means? Why that 3 becomes 0? Yeah, direction. Yeah, since these vectors are just only directions only happen. Only rotations only happen. So it is only necessary to mention only the direction of that. So that's why it is 0. Why it is 1?
Distance, same distance.
Yeah. So you're not scaling up, it will be same only. So the representation of matrix like this, this is now a 4x4 matrix, right? 4x4 matrix. So representation of matrix like this is called an homogeneous matrix. So representing this matrix in this form, it will be very easy for calculation. Representing a square matrix, we can represent the f also with this also. That means 4 by 4 matrix. 3x4 matrix we can represent, but that won't be a square matrix. So while finding inverse and all those things, it will be difficult. So this addition can be also taken. So it makes 4 by 4, and that matrix is called a homogeneous matrix. These are the properties. As I said, the modulus of this will be 1, modulus of this will be 1, modulus of this will be 1. So that is the first property. And since this is also a frame, frame means they are mutually perpendicular to each other. So N, O, A. So N dot O will be 0 as angle between them is 90 degree. N dot A will be 0. Similarly, A dot O will be 0. And we all know that I, J, K. So I cross J will be K. Right? Similarly, N, O, A. N cross O will be A. That will also possible. That we mentioned. Okay, now let us consider one point already there in space. It has some, this is a point, this is a point, so this is A, N, O, A, X. Okay. This is a point. This is already there. It has already translated as well as oriented also to some angle and some distance away. Let it undergo further translation. Let it be D with respect to this fixed frame. This is the fixed frame. Okay. All these things are happening with respect to the fixed frame. So let that translation, that D translation from here to here, we can represent it by distance will be dx, dy, dz. Why this become 1, 1, 1? Yes. Same that. Yeah, no angle. Yeah. Yeah. That is, I think you know that math, right? Why it is become 1, 1, 0, 0, other than 0. Actually, this should be nx and ny, n is right. Ny and nz are 0, nx is only 1. It is actually collinear. When one vector is collinear with the other, it doesn't have any component in the other to that. So, taking it is again on the nx also a unit vector, so it will be 1. That way. So, while it is just translation is only happening to that, this matrix will be like this only 1 0 0 0 1 0 0 0 1, and the other will be dx dy dz and 1. So this is the translation happening, and the existing point will be this is our old thing, nx, ny, nz, ox, oy, oz, ax, ay, az, and px, py, pz 0 0 0 1. This is the existing point. To this existing point, that D translation happened. So that is the translation mentioned here. So in order to get the position of the new point, this is the new point, right? New point with respect to the reference frame or fixed frame, we will pre-multiply this matrix with the existing matrix. This is the F4. Same matrix. We will pre-multiply. Any translation happening with respect to the reference frame, we will pre-multiply. So that is the concept. Pre-multiplying only, we will get the result like this. So the orientation will be same as the previous frame itself. Nx, ny, nz, ox, oy, az, ax, ay, az. They are also same. Only it is get translated. So it's px plus dx, py plus dy, pz plus dz. Here you have to multiply. Multiplication, this is just a multiple multiplication. This thing with this, will multiply. So you can write the new as new value for the vector will be equal to translation dx dy dz times f4. So that should be pre-multiplied. Now we can see about the rotation. Last time we see translation. Now we can see how rotation is happening with existing objects. So, okay. There is a fixed frame fxy z. So this is small frame, NOA frame, NOA frame, and I've seen a point P. This is a point P, which is attached to the NOA frame. So with respect to the NOA frame, I can write this vector like Pn I cap plus O j cap plus A j cap, k cap. Right? With respect to the smaller frame, if I have a smaller frame, I have a point, I can mention its own frame, right? If I have a bigger frame also here, I can mention the same point with respect to the bigger frame also. So in terms of bigger frame, it will be Px I cap plus Py j cap plus Pz k cap. Difference is representing the same point with respect to different frames. And assume that this frame, the smaller frame, actually everything is parallel. That n is parallel with respect to x axis, and this is that, right? This is that. So a axis is parallel with z axis, and o axis is parallel with the y axis. Actually everything is parallel on small positions. Let it undergo a rotation about the z axis and angle theta. This frame is undergoing a rotation. So this is the rotation that undergoing theta. Not with respect to x axis. Okay. With respect to x axis, the other frame is rotating. Just an angle theta. So it will make an angle theta with respect to y, and similarly the n. Okay. The axis also make an angle theta with respect to z. Just a rotation. Understood? So this is actually the bigger figure, enlarged figure that you can see there. So when this thing is rotating with respect to the x-axis, the n will be parallel to the right. N will be parallel to the x-axis. So that is usually out of the box, which is not shown there. So that is not required because that is already putting in. Other two points are this is O, this is A, this is Y, and this is Z. Yeah. You can see the bench. Okay. So this is the point P. I said that is P attached to a smaller frame. Okay. So the distance, this will be Py. It means the position of the point P in the y direction with respect to the fixed frame. Then this will be Pz and Pa. So you can see it. This is PO, is also PA. This is a frame, so this is the distance in the A axis. This thing only, PA, same thing only, PA, then so that is the same. This is a point, and those are the it's like the components in the different axes. PA along the A axis, PO along the O axis, PY, capital PY along with, that is with respect to the reference frame, that is PY, and PZ that is along the Z direction, what is its component. That way. Actually what we are going to find is that we are going to derive a relationship between Pxy, that point Pxy Z, and with respect to Pnoa. That means we define the same point with respect to xyz axis as well as Noa axis also we define the same point. So we need to find what is the relation between P x, y, z with respect to P and Y. So that way we are doing this. So here you can see, since it is rotating with respect to x-axis, the x and n-axis will be collinear. So whatever be the position, it will be same only. Second, Py. Py you can see it will be L1 minus L2. So in the figure, this is L1 and this is L2. So Py is this thing. Py can be, this is L1, okay? This is L1, this is L2. So Py will be L1 minus L2. So that can be represented as P0 cos theta, because L1 is this is theta, and this is L1, right? L1 can be P0 cos theta. L1 is P0 cos theta, because theta is P0 cos theta. And L2 is, this is the distance. So if this is theta, this will be also theta. So it will be PA sin theta. Yeah, PA sin theta. So PA cos theta minus PA sin theta. Similarly, we write PZ. PZ will be, this is L3, this is L4. So L3 plus L4. So that can be written as P0 sin theta plus PA cos theta. That you can be derived from the figure. So now, when we are representing in the matrix form, it will come like this: Px, Py, Pz will be equal to. Now, for this thing there is no cos and sin terms. So initial thing will be 0. There is no cos and sin term. Next is initial is, this is Pa and there is no cos and sin terms. Okay. At the bottom, it will come, here it will be 0 because there is no constant term. So next will be P0 cos theta, other will be minus P sin theta. This PA sin theta, PA sin theta. This is P0. And third one will be, again there is no constant term, so it will be 0. So it will be P0 sin theta and PA cos theta. So this is the method of representation. To simplify it furthermore, we can take the P0 common. Here also PA also common. So that is been taken out and this is the final matrix. You can multiply it. This thing multiplied with this will come as Pn. Then this thing will be, this will be 0, so it is P O cos theta minus PA sin theta. Again, this will be 0, then PO cos theta sin theta plus PA cos theta. So that is a matrix representation. So actually, this is the transformation matrix that will convert a point in, P and Y axis to Px, Y. Initially I said there is a fixed rate x, y, z. There is a moving frame, NOI frame. Okay, it's not clear. And I have a point P which is attached to the. I am defining that point with respect to the NOI frame. So that will be P N, P A, P O, and O A. P A. I cap, J cap, K cap. Okay. So I have this point, this P point with respect to the moving frame, the smaller frame. I have that. So if it undergoes a rotation with respect to the x axis, so that was our rotation that happened to this frame. It is rotating with respect to the x axis to an angle theta. Okay. So your aim is to find the what is this point after rotation with respect to the x axis. That is with respect to the this frame, x y z frame. You have to find the coordinates of that point. After rotation, what is the coordinate with respect to the reference frame? So that you will get by P x by z. After rotation, in order to get that, we just need to provide this matrix multiplied by the what is the value that is attached with the f and y frame. So you will get the new position with respect to the reference frame. Okay. You understood? This is a simple thing. There is a rotation happening to that thing with respect to x-axis, and we know the position of that point with respect to the smaller frame, that NOI frame. We know that. So we need to find the what is its point after that rotation. X one rotation. X with respect to x1, there is one rotation happening. What is that point with respect to the reference frame? We need to know that. In x how much it is, in y how much it is, in z how much it is. We need to know that. So this is the matrix that we need to multiply with the point that attached to the x and y frame. So after the rotation with respect to x-axis, the new coordinate will be this. You will get p x and p, px, p and pz. 3 by 1 matrix you will get. So that is the point. So we see the transformation. This is the transformation matrix for the rotation along x. Rotation happened with respect to the x-axis by an angle theta degree. So that is same thing only. Rotation about x by an angle theta degree. Similarly, we can derive for rotation. What if the rotation happened along for y axis? Similarly for z axis. This is the same thing. About the point. Now we can see one example. Assume a point. This is the point. 7, 3, 1. So that point is attached with the FNY frame. This is FNY frame. This is a point. So it is subject to following kind of transformation. First is rotation 90 degree about the z axis. Rotation about z axis 90 happened. Second is followed by the translation 4 minus 3 7. So translation 4 minus 3 7. So it is followed by the rotation 90 degree along y axis. So rotation along y axis by an angle 90 degree. These are the three transformations that happen to that point. And that point is attached with the FNY. Attaching means that point is referred with respect to the FNY, not with respect to the reference frame. Okay, so this is the representation, means diagrammatic graphical representation how the transformation has happened. So it's not clarified, right? This is x, this is y, this is z, this is n, n1, this is n1 over 1. So that figure says about the first thing, that is rotation about the z axis. Initially, its position will be in this direction, right? That y-axis will be along this direction. So all are collinear, all are aligned with each other. When it undergoes a rotation with respect to z-axis, because with respect to z-axis it is rotating an angle 90 degree. So after it got rotation by 90 degree, the y-axis will be in this direction. So that is the first. That is represented by this. And in the second figure, it represents the translation of 4 minus 3 7. So the frame is actually translated. Okay, with respect to this frame, reference frame. So it is moving 4 along the x-axis. This is x, this is y. Okay, moving 4 distance along this direction then minus 3 in the y direction, z along 7 in z direction. So new position of the frame will be here. That is also simple. Third thing is the rotation of that point with respect to y axis. For that thing, you need to assume this thing, right? It is moving minus 3. So enclose it in some kind of a cuboid, and the cuboid need to rotate with respect to the y axis. The cuboid is actually rotating, so that 4 will come here, 4 will come here, 4 will come here, and minus 3 will be here, and the 7 will be here, and we have our entire frame here. The cuboid you need to rotate. That is for simplicity only. You may not be rotate correctly. So I said if we consider enclosing the cuboid and rotating, you will be correctly. That 4 will come down. After 90 degree, it should come down, right? Should come. Then this will also be. This will be a 3 will be around this level. Exactly here. Is okay. And now we can say about the point P. Point P is 731. It is attached to this smaller frame. So this is a smaller frame now. Our smaller frame is here. So that is with respect to that frame we know the coordinate. That is 7 along the n axis. 7 along n axis and 3 along o axis. This is o axis. This is o axis. So 3 along o axis. This is 3. Here one small one unit. That is along the axis. So that is our final point. This is our final point. P. That's the final point. So now, from the figure itself, we can say what is the position of the point P with respect to the x, y, z. We know what is the coordinates of the point P with respect to. This is 731, and we done all this rotation, translation, all is done, and we got the position. We know that now currently the P is there, so we can find what is the coordinate of the P with respect to x, y, z axis. So that is it is 7. Here it is 7 plus this one is also there, so it will be 8. Then now in y it will be 4 goes down and 3 up. So it will be y is this direction. Here it is 3 along this direction, and the P is actually located 7. Yeah, here it is 7. So 7 minus 3 will be 4, and along the Z it is minus 3 down and 4 up. This is 4 up, so it will be 1. No, it's minus 4, and that is that is 3, and that is minus. You will get the same formula. So doing this thing by doing graphically is a difficult thing. If you need to draw the figure, you need to find. So rather simplified method is multiplying the matrix. So there is a point P N O A, and it's P N P O P Z. Represents 7 3 1. We have the point. So whatever the transformation that happens with respect to the reference frame, that will be get pre-multiplied. Okay, pre-multiplied. It will get pre-multiplied. So the first translation that happened with is the rotation with respect to Z axis. So it will be rotation with respect to Z axis. Pre-multiplied. Next will be followed by the translation 4 minus 3 7. Translation 4 minus 3 7. Pre-multiplied. Again, last will be rotation about y 90 degree. So y 90 degree. That is also pre-multiplied. This will give a new transformation matrix. or new point with respect to x, y, z axis. That is actually not here. Y translation. These all metrics are multiplied. We know what is y x90. Substituting c theta means cos theta for simple representation. Sin theta means s theta means sin theta. Understood? So cos theta will be cos 90 0. Putting that thing, you will get that matrix. What is that matrix? So that will be substituted, and you will get what is y with respect to 90. The translation means other will be just 1 1 1, and this command will be there. Similarly for rotation about this axis, again the matrix is there. Substitute that 90 degree, you will get corresponding matrix. And multiply it by finally that point that will be NI 3731, and the scale factor will be 1. And we will get the new position 8 4 minus 1 1. Then you can see. So, and with one more example. I am not going to explain the graphically. Okay, it will take time. Assume the same point means 731, right? P 731 was our point. That is attached with respect to the NOI effect. It is attached to the NOI effect, which undergoes rotation of 90 degrees. Now it is not with respect to XY axis. It is with respect to A axis. Okay. Translation 4 minus 3 7. That is also happened along NOA axis. So earlier those translation rotation happened with respect to this frame, XYZ frame. Now it is also possible for the translation to happen in NOA frame also. It can translate, that frame itself can translate. It can rotate its wings on axis. And followed by rotation 90 degree along O axis. So if rotation happened with respect to the moving frame itself, that means if NOA frame itself, we will post multiply everything. Instead of pre-multiplication, we will post multiply. So we have the point at P NOA that first will be R90 rotation about 90 degree with respect to the A axis multiplied by translation of 4 minus 3 7. Then now it is post multiply, not pre multiply, followed by the rotation about the O axis 90 degree. Then we will put the point P and O. So this will generate the new coordinates. P in terms of XY axis will generate the coordinates. If rotation happens with respect to the NOA axis. So this representation is seen here in this figure. We will get the same coordinates 0 5 0 1 there. Do you find any difference? Earlier the same. Earlier also there was same angle change was there, but that was with respect to XY axis, and we got a result like 8 4 minus 1 1. That was our coordinates, new coordinate with respect to XY axis. Now all the transformations have happened with respect to the its own axis, means moving axis, NOA axis, and the coordinates are 0 5 0 1. They are not same. That is actually this is a combined means motion happened at along with respect to XY axis as well as NOA axis. So here there is no point attached to the frame. You just need to say about only the matrix only. So a frame of F is there, so which undergoes around y axis undergoes rotation. So rotation along y axis 90 degree. Followed by rotation about the O axis. Rotation about the O axis 30 degree. followed by translation of phi unit. Translation of phi unit along n axis. So phi 0 0. NOA. So phi 0 0. Finally, the translation of 4 unit along x axis. So 4 0 0. These are the transformations. These are the transformations that happen to the F matrix. F matrix means FNOI matrix. This is the reference line. This is the FNOI. This much rotations and translations happen to that way. So you need to find what is the total transformation matrix. So what you will do is that anything which happened with respect to the reference frame will be pre-multiplied. Anything happened with respect to the its own frame, going frame, it will be post-multiplied. So first will be rotation. First transformation is the rotation with respect to the element. First transformation is the rotation with respect to the y-axis 90 degree. So I wrote like that as well. Next will be rotation about o-axis. So it will get post-multiplied, post-multiplied. So rotation about o-axis 30 degree. Next is translation that happened along n-axis. So that is also its own axis. So it will again get post-multiplied. Translation 5 0 0. Next is translation of 4 units that happened along x-axis. So that is with respect to the reference frame. So we will re-multiply that. 4 0 0. So multiplying all this matrix, you will get a new transformation. And if any point is attached with respect to FNOI frame, if you are multiplying with that frame, that point also you will get a new point with respect to the x y z. Okay. Now let us look how to find the inverse of a matrix. So this is a general transformation matrix. It has orientation, nx, y, or x, y, z. Some translation are there, basically. So how to write the inverse of that matrix? So we learn some adjoint J by determinant J, that was one of them. So for finding a homogeneous matrix, the inverse is much more similar. You can easily find. That mother is okay, but that is too tending. So the mother will be, the inverse will be equal to R transpose minus R transpose dot P 0. So this R is basically this matrix. Its transpose is written here, and the R transpose is multiplied by the Px, Py, Pz. So that is being represented with a minus. This thing represents 0%. So that's a way to find the inverse of the matrix. You don't need to do adjoint and determinant. Now we will discuss about the forward and inverse kinematics. How to find the forward and inverse kinematics for calculation. So there are few methods are there. So one of the widely acceptable method is DH, the hardest representation. So in this representation, I showed you one 2D of manipulator type. There is a 2D of manipulator. So these are join 1, join 2, this kind of vector. So in this method, we will assign a frame to each joints. So assigning of the frame means actually 3 axes like x, y, z. They are mutually perpendicular to each other. That thing is called a frame. So we will assign a frame. So there is a procedure to assign the frame. We cannot simply assign the frame. So that is first thing. We will first assign the frame to each joint. Second thing is the then we will write the transformation. Once the frame is assigned, let this be the frame assigned. Once frame is assigned, we will follow some procedure to transform from this frame to that frame. There is also procedure, so that's the second thing. And finally, we will multiply all those transformations to get the total transformation matrix for the. So that is followed in these matrix. So consider a general case. This doesn't actually represent the real robot, but this is only a general case. So this is one joint, and this is the other joint, this is the other joint. Okay. So the first thing we need to do is that assigning of the frame. Frame to each joint. Assigning of the frame to each joint. We need to do that. So we will start with assigning of Z axis. So the direction of the Z axis will be direction of the motion of the joint. Since this joint, you can see, it can rotate like this. So right hand will move up. So that will be the direction of the Z frame. So since this is a general robot, it consists of so many links, so many joints. Assume like that. We are just taking in between some links and taking end the joint, end plus one joint, end plus two joint. Just for reference. It's a general thing like that. Okay. So this frame. First we will assign the Z axis, so that will be given by the right hand thumb rule. So since this joint is moving like this, so when you rotate it with your hand, it will move up. So that is Z n minus 1. The end joint is represented by n minus 1. Z n minus 1. 1 minus 1 will be there. Similarly, for the next thing, that is next joint is n plus 1 the joint, and here it is like this, and rotation is happening like this. So again, right hand thumb rule is pointing in this direction. So that will be Z n plus 1 to joint, Z n 1. Okay. Next will be n plus 2 joint. This is pointing like this way. So right hand thumb rule, it will be pointing upward. So Z n plus 1. Z n plus 1. So assigning of the Z frames are done. Next will be the assigning of the X frames. Usually the X will be in the direction of common orbital distance between the two joints. Common orbital distance means this is the exact Z axis, right? Z from axis. This is the Z n axis. So there will be, so these joints are like this. You are visualizing 3D. So there will be at least one point you can draw a common orbital distance, right? If it is exactly like this, there is infinite number of normals. Many joints you can draw. If it is like this, there will be at least only one. It can be crossing also. This is crossing. You have to think in 3D. So this is actually happening here. So this is here. This is breaking like this. It is breaking. So there is at least one common orbital distance will be there. That means the shortest distance, that is perpendicular distance that you can draw between the two lines. Yeah. If two parallel lines are there, the common orbital distance between them is this thing, that is shortest distance. Similarly, in the case of here also, common orbital distance will be there. You can write perpendicular distance anyway. That will be the shortest. So that is A. That is the common orbital distance that exists between Z n minus 1 to the frame and Z n frame will be called as A. Similarly, for the Z n and Z n plus 1 frame, there will be a common orbital distance between those two Z axes, that will be called as A n plus 1. And the direction of the X n will be in the direction of the A n. And the direction of the A n plus 1, X n plus 1 will be in the direction of the A n plus 1. So Now assigning of the x also done. Z is done, x is done. Why will automatically be done? Because they are mutually perpendicular to each other. X, Y, Z are mutually perpendicular to each other, so it will be automatically done. That is what we learned. This y they are mutually perpendicular. Next is the transformation. Means after assigning of proper frames to the each joint, just we need to find a transformation matrix. Means we will transform from this joint to this joint, this joint to this joint. Okay. If a robot is there, again the same 2 degrees of freedom theory. So we will first transform from here to here, then here to here. This is the base, and finally we are finding what is the transformation from of this thing with respect to this. That is actually we are finding. So there is a procedure to write the transformation of it. I will discuss. Let us do some notations of it. So theta be the angle, the x-axis will rotate such that the x-axis become parallel. I don't think you. Vendra and Viren is also having, so you can ask them also. And they are also taking this course. Now first, there is only 4 parameters in case of pH matrix. So that will be theta, d, a, and alpha. So what theta will represent is that it is the angle that z-axis need to rotate to make this xn and xn plus 1 parallel. Okay. Okay, I will simplify this figure. This part is here. This simplified figure is this figure. First part. So okay, let theta be there. We can discuss about d. D is actually the distance between this is the distance along the z-axis. Along the z-axis, that is between the two common number distances, xn and xn plus 1. That is d. D n plus 1. This is the distance. This is xn. This is xn plus 1. Right? This is xn plus 1. So the distance between them around the x-axis is d n plus 1. Next is a. A is the length of the common number. We discussed that length of the common number is the distance between two x-axis. So this is a and this is a n plus 1. Alpha is the angle between two z-axis. This is z axis and this is n plus 1 axis. So these are the 4 parameters that are involved in a DH matrix. Okay. So first step in DH is that assign the frame. After that, we need to get the transformation. For doing the transformation, first step will be aligning the x-axis parallel. For doing that, you need to rotate theta. This is a simplified figure of that last two joint I showed. So this now the xn is like this. This is xn plus 1. So if you rotate this theta n plus 1 such that they should be aligned parallel. So xn and xn plus 1 will be parallel. So that is the first step. Next is the here is that point. Okay, here is the next point. So actually we are doing translating from here to there. So first is aligning the x-axis parallel. Next is the motion moving along the z-axis to a distance dn plus 1 such that the point will come here. Now the point come here. It moved a distance of dn plus 1. Okay. Next translation next will be motion on the x-axis an plus 1. Then the point will come here. It came here. Next, there is an angle between z plus 1 axis and z axis, that is alpha n plus 1. So you need to rotate that also. The Z need to rotate an angle of alpha n plus 1 to perfectly match with the Z plus 1. So that both the frames are completely aligned. That is only the thing that we are doing. We are, if one frame is here, one frame is kind of something here. So we are making this frame to there. So in order to do that, there is only 4 parameters according to dh. That is motion along. First is rotating the theta with respect to z axis such that x axis will become parallel. Okay. Then rotation, not rotation, translation along this axis dn plus 1 so that it will reach here. After that, you need to move an plus 1 along the x axis to reach here. Let me represent here. Now there is an angle between z and z plus 1. So z need to rotate an angle alpha n plus 1 to completely align. So this frame will be completely aligned like this. After doing all these 4 steps, it will be completely aligned. These are only the 4 parameters for this transform. Common for all. As I said, so now we can write the transformation, right? One, let us see being transformed. So we can write the transformation. So first thing is the rotation about z axis theta n plus 1, such that the x axis becomes parallel. Second, translation along the z axis dn plus 1. Okay. Next will be the translation along the x axis n plus 1. Next will be rotation about x axis n plus 1, such that both the frames will be completely aligned. That means if there is one frame, initially it was like this. After doing all this transformation, it got aligned completely like this. Completely aligned. So that is being represented by, if the smaller frame is represented by n, this n plus 1 the frame. So n plus 1 representation. From n to n plus 1, what is the transformation? That is also represented by a n plus 1 also. First thing is the rotation with respect to theta, z axis, theta n plus 1. So we know the transformation matrix that we learned before, rotation about z axis. This thing. Rotation about the z axis. This is the transformation. Same thing only. Here we are putting theta n plus 1 is the angle that we need to rotate. So we put the theta n, substitute the theta n plus 1, theta n plus 1, we get the matrix. This is the translation along the z axis. So 0 0 n plus 1. First will be one additive matrix. Next will be translation along the x axis. N plus 1 will be like that, and other will be rotation about the x axis. Saying that rotation x theta, here the angle is alpha n plus 1, which is being rotated. So multiplying all this matrix, you will get a matrix like this. This matrix we need to know. The exam point of view, they said you need to by heart. This is cos theta n plus 1, sin theta n plus 1, 0 0, minus sin theta n plus 1. Cos theta n plus 1, cos theta n plus 1, cos alpha n plus 1, sin alpha n plus 1, sin theta n plus 1, sin alpha n plus 1, minus sin cos theta n plus 1, sin alpha n plus 1, cos alpha n plus 1, 0, n plus 1, cos theta n plus 1, n sin theta n plus 1, dn plus 1. It's a matrix. Because in order to represent a transformation from if one frame is there, one other frame is here, in order to represent a transformation, you need to write this transformation matrix. That's the example. Then we go with the example. So you can take a robot, a manipulator. 2 degrees of manipulator. This is a 2 degrees of manipulator. Base of this can rotate like this can rotate like this, and this is the end of it. Okay. By writing the DH, we usually follow the simplified representation. We will stretch it along this direction. So simplified representation will be, we will just put dots for joints, and links we just usually mark L1 and L2. This line is related to this will be EA1 and this will be A2. Okay. So the simplified representation will be, this is the first joint, this is joint 1, this is joint 2. Okay. So this is joint 1, this is the joint 2, under dot, and the also we will put under. Simplified representation. And what is the first step while dealing with the DH? Marking of its frames. So we will start with the assigning of Z frames. So this thing is rotating like this, right? So when you take the right hand rule, it will be either into the plane or out of the plane also you can take. So this is, I am taking it as out of the plane, out of the board. Z0, marking Z0. First joint marked by, if the joint is first, then the frame will be, joint is n and the frame will be n minus 1. So if the frame is, if the joint is 1, then the frame will be 1 minus 1, then it will be 0. That frame is 0. First joint, 0. This is 0th frame, you represent frames like that. This is first frame, this is second frame. And the fifth also will be marked with frames. This is first joint, second joint. So this is the Z0 axis. Next is second joint. So that is also either into the plane, out of the plane. You can move like this. Okay. So I am taking, since it is rotating like this, I am taking out of the plane. You can take into the plane also. But I used to take outside the plane. So this will be Z1. Second joint, 2 minus 1. Z1. Here, assigning of the things end effector is not a joint. So the direction of the Z frame for the end effector will be same as the previous joint. Okay, same as its previous joint. So if the direction is along this out of the plane, out of the board, so its direction will also be out of the board. Z. So after the Z axis are marked, now we need to mark the X axis. X-axis direction will be in the direction which is perpendicular to is a common normal distance between the two Z-axes. So these are the two Z-axes. The common normal distance between them is this, right? So X-axis will be Z0 and Z1. These are the Z-axes. So the common normal distance will be this only, right? So between the Z0 and Z1, this will be the distance, common normal distance. So you can mark the x1 in the direction of common normal distance. Okay. And x0, this is a starting point. We don't have any joint before it. So it is an arbitrary. You can mark in any direction. So I am marking in the same direction as x1. So this will be x0. Between Z0 and Z1, if there is common normal distance is there, along the direction x1 will mark, and x0 will be arbitrary because it is the starting point. So you can mark in any direction. I am taking the existing direction, x1 direction to x1. Now, inductor will have a direction that is same as the previous point. So its direction also will be around this direction. Y axis will be automatically aligned because they are mutually perpendicular to each other. So frame assignments are also done, and the distance, since these points we are assigning the frames, right? So distance between these two frames will be A1. Distance between these two frames will be A2. This is a simplified representation. Okay. Now we need to write the DH table. So DH table is essentially for writing the matrix only. So we need to write. So here will be joints bar link. So 0 to 1 means 0 to 1 is join, and this is link, and 1 to 2. H is 1 to 2. H is same as 2 volt. Okay. 1 to 2. This is 0 to 1. Okay. For approximation. There is what actually happening is here is that here there is one frame, right? Here is one frame, and here is also one frame. So we are shifting from this frame to here first, then shifting from this to this. Only two transformations. So that's it. 0 to 0 1. In this, we will write under theta. These are the four transformation cycles. That is motion along the z-axis, tan angle theta, then translation along this axis by d, then translation on the x-axis by an plus 1, and the angle between this axis is alpha. So these are the four transformations that are happening to represent the transformation from one to the other. Okay. So first will be theta 1. First will be theta 1 because this is theta 1. Okay. These are pointing off. This will be theta 1 and theta 2. These are the so you should need to rotate an angle theta 1 such that the x-axis will be aligned. It is the same concept before. This thing only. Discussing only this thing only. But to make it simpler, we are converting to this format. So you don't need to overthink that. What is the math happening behind it? So once you get practice, you don't need to think that figure also. So that's the translation transformation. You don't need to think. You can directly do it. So first is this joint is there. It is moving an angle theta 1, right? So it is moving an angle theta 1. Yes, along the D. Along this, if there you have to check that if there is any motion happening along the z axis. Since this is the x axis, right? So there is z is along this. So in order to move this frame to there, it need to move like that. So the motion is only along the x axis. So z axis motion is not there. So it is 0. Next, A is the motion on the x axis. Since this is the A1, in order to move this frame to there, you need to move a distance of A1. So it will be A1. Next is alpha. Then you should discover that is there any angle between these axes? Because this is 0, this is 0. Then you put this frame to there. First we rotated and we moved to this here. Now I can see that these Z0 and Z1 are already parallel. I don't need to. There is no angle between Z0 and Z1, so that will be 0. Similarly, so this is done. Shifting from here to here is done. Okay. Next is here to here. So here also rotation is there. So after that rotation, the x-axis, x1 and x2 axis will become parallel. Okay. In this figure it is already parallel, but it is not like that. This is a simplified representation. That's why it is like this. You have to think that, assume that it's the correct thing only. If you come to me personally, I will explain how that is happening. So this is a simplified representation, not to confuse you and all. So after theta 2 rotation, x1 and x2 become parallel. So theta 2. Next is the motion along the z-axis. Check whether any motion on z-axis. In order to move this frame to this here, is there any motion? No, because this is x1, z1 is here. So there is no motion on the z-axis. Means z1 axis there is no motion. So it will be 0 length. Then motion on the x-axis. In order to move from here to here, it need to move at distance of a2 along the x1. So it will be a2. Then once it moved completely here, you have to check whether there is any angle existing between z1 and z2. Not there. So that is 0. So this is actually base representation in table format. Okay. Now said about this thing, right? N T n plus 1. So I need to first need to do either 0 to 1. So 0 T 1. Sorry. 0 T 1. So you will substitute. So now n become 1. So n is 1. N is 0. 0. This is n T n plus 1. So for 0 T 1, n should be 1. So first we need to substitute this matrix. This is a final matrix. This is a final matrix. You need to substitute the n into 0. So it will be cos theta 1, theta 2, like theta 1 like that. So like that, I can substitute in that matrix. This n plus 1 matrix is there, right? I am substituting in that matrix. I am getting A1. A1 is actually n plus 1. When you put n is equal to 0, it will become 1. A1. So the first matrix A1. By substituting these all values, I am transferring from here to here first. So you need to use first this thing. For the second thing, from transferring from here to here, you need to use this thing. You need to substitute these values in that matrix. So you will get A1 and A2. That basically means transformation from 0 to 1, then transformation from 1 to 1. In order to get the whole transformation, we will just multiply. Means I need 0 T2 from base to 2. This is base, this is 2. Right? From base to 2, what is the final transformation? That is 0 T1 multiplied by 1 T. So when you multiply both these matrices, you will get the 0 T matrix. That is the transformation. Not expecting.
Actually, I was creating on video. Can you show that? Go visual.
Should I show now? What's up?
This is simply describe the motion of a series of linear joints. This is useful for efficient calculation of fluid and inverse kinematics. The process begins by defining the z-axis along the axis of rotation for regular joints, or the axis of translation for prismatic joints. Since this is the first joint, the x-axis is a free choice. For later joints, each x-axis will point away from the previous joint. The y-axis simply completes the right-handed reference frame. Now if we add another joint, we can determine the transformation between them. As before, the z-axis points along the axis of rotation. The dh parameters will be derived from the common normal between these z-axes. The common normal is orthogonal to both vectors. It's also the shortest line between them. The new x-axis points along the common normal and has its origin at the intersection of the new z-axis. Notice the origin is not within the physical actuator because the dh parameters are only concerned with the motion of the links, not the physical placement of components. Using this protocol for laying out the reference frames, only 4 parameters are needed. The first of these, d, is the depth along the previous joint z-axis, from the origin to the common normal. Theta rotates about the previous z-axis to align the x-axis. R is the length of the common normal itself. Most texts call this parameter A, which is unfortunately easy to confuse with alpha. Instead, calling it R is astronomic, as this is also the radius of revolution for the new origin about the previous z. Finally, alpha rotates about the new x-axis to bring z into alignment with the axis of joint motion. Now there's one special case, when the z-axes are parallel. Because parallel lines have an infinite number of common normals, you can choose any d value you like in order to place the new origin at a convenient location, such as the center of a link or the tip of an end effector. The other parameters are the same as before. Theta rotates about z to align the x-axis with the normal. Then R translates out along the normal to reach the new origin. Alpha is already known to be 0 in this case, since the z-axes must be parallel for this to apply, thus no rotation is needed.
This is actually the whatever the transformation is, right? The motion, rotation on the z-axis, rotation on the x, rotation along, motion on z by n plus 1, motion on the x by n plus 1, and rotation on the x by n alpha n plus 1. These are the things. It's visualized. Okay, and now discussing this is the scalar about itself before the year. So now discussing. Now we can go with the inverse kinetics. One more thing. So now we have the final matrix, right? From this 0, T1 multiplied by 1 T2. And T2 is the final matrix, final transformation matrix that we have. So in order to and this was our robot. This was my robot. Okay. So there is a frame attached to that. Everything for every point there is a frame attached to that. So I have one point P which is attached to this frame. Initially, I know it can be some tool or something. Tool means some train something, some tool. That position I know. So that is being defined with respect to this small frame. I know the position. So if I multiply that P and O, with smaller matrix, after and I am providing C12 is actually cos theta 1 plus theta 2. Okay, theta 1 and theta 2 are the angles that these joints are rotating. Okay, so forward kinematics means I am providing the angle theta 1 and theta 2, and I should get some position. If we provide an angles here multiplied by P and O, I know here starting or I know the position of that thing. So I will get the new position after this theta and theta. What is the new position? So that is the forward kinematics. That means I am getting the position x, y, z of that particular thing. If I give this joint angle, I will get the position of new thing. Means I have okay, this is my hand, right? This is my hand. So similar to that thing, there are rotations to our hand. Here one rotation is there. Short also one rotation. Actually, this is not 3 degrees of freedom. The degrees of freedom is much more. Can you say how many degrees of freedom our hand have? there is rotation here, like this is there. This is also possible. Here itself 2 degrees of freedom. Here 1 degrees of freedom. Here 1 degrees of freedom. Till here it is 1, 2, 3, 4. 4 degrees of freedom. Then our fingers are 1, 2, 3. Again degrees of freedom. Each finger are 3 degrees of freedom. So when I am restricting to 3 degrees of freedom, that means motion is only along this. Sorry, this is the end effector. Okay. In order to, if I provide an angle, means if I provide theta 1 to here, theta 2 to here, this is the end effector, right? So I will get a new position. By providing the angle, I will get a new position where it will go. That means I can check if I provide theta 1, theta 2, what is the new position in future. That is actually basically the forward kinematics. Giving the joint parameters and getting the coordinates, x, y, z coordinates. Inverse kinematics is actually the reverse thing. I need to go to this projector and click some button. So in order to do that, what are the angles required? What is the theta 1 and theta 2 required to get that to move that position? For that, I know already the position and the orientation. Okay, that's inverse kinematics. So how to find the inverse kinematic solution? Means you need to find the values of theta 1, theta 2, theta 3. If there is, if you have a point in space, you know this is the px, py, pz point with respect to the one. If there is one world frame is there, okay. There is one point is there. Here our robot is also there. Some kind of robot is there. So with respect to the world frame, that is the reference frame, I know the position. What is the final position that I am desiring? Px, py, pz, and orientation also. Assume that it is a kind of a bulb. Okay, the robot need to hold that bulb. That is our task. So this bulb has some kind of one orientation is there. So that is represented by NX and by NZ. There is also one frame is attached to it. So because of that reason, I can represent its orientation NX and Y, NZ, OX, OY, OZ, AX, AY, AZ. As well as I can say this is this much distance from reference frame, that is in X, Y, and AZ, whatever the distance. So this is the orientation that I know. This is the desired position. I want my magnet to go there. So since we want to find the final transformation matrix, like 0, T2 from the previous example, that was our final transformation matrix. So if assuming that this is the final transformation that we get, we just need to equate that. Only that is required. Equating that, because I know the final orientation, final position that is required, and I have the final transformation matrix also. So just equate that, then solve. You will get the answer for theta 1, theta 2, theta 3. For doing that, simply equating, you won't get the answers. You have to use a function called a tangent function. A tangent function is same as tan inverse, but it is more kind of a programmatic manner. In programs, we use that a tangent. So I am just explaining that function. So inside the a tan 2 function, you want some sine function, we will call sin x, then cos x. Only that much is required. Some values will be there, because a tan 2 is similar to tan inverse function. So tan inverse of sin by cos what? Sin by cos theta. Sin by cos is tan. So tan inverse of tan is that's what happened. So comma is divided by x. This is a programmatic way, I said, right? So a tan 2 sin x by cos x. So that will provide the theta. But assume that it provided theta, we will get a theta. We get theta. Now I am representing this. There will be some value also there, right? Over here tan 2 the sin x of some value, let it be called as a11, and cos x of some value be called as a12. Okay, so this will provide the theta. Here we need to discuss all the cases based on the signs of a11 and a12. First we can discuss if a11 and a12 are positive. If a11 and a12 are positive, a11 and a12 are positive, both are positive. You need to find the tan inverse. You need to find the tan inverse of a11. Take the modulus a11 by a12. You need to find that value. You will get a theta. You will get some theta. You will get a theta. And if both things are positive, that means sin and cos are positive. Sin and cos are positive means they are lying on the first quadrant. So you can write the same theta. Same theta. Don't do anything else. Next case is when a11 is negative and a12 is positive. Which values are negative and other is positive. Similar way, you find the value of theta, that is tan inverse of, take the modulus a11 by a12. This is the modulus value. Take that value, you will get the theta. So a11 is negative means sin is negative. Sin is negative and cos is positive. Which quadrant? Okay. So it will be minus theta. Theta will becomes minus theta. Similarly, if this is negative, if this is positive and other is negative, find the tan inverse like the same way. Take the modulus a11 by a12 tan inverse, and sin is positive, cos is negative. Which quadrant? Second quadrant, it will be theta will become 180 minus theta. Second quadrant, right? 180 minus theta. And if both are negative, it is third quadrant, right? So we will get a theta by finding tan inverse a11 by a12. So the theta is in third quadrant, so that means 180 plus theta. I can write the theta 180. So there is a function. The functions or libraries are available when you are dealing with such functions. So when you directly provide a tan2 with some parameter value, it can automatically give this value. You don't need to do it manually. Okay. And we are using a tan2 function to find the angle. We do not directly substitute and find that. If we know sin 12, we know that ny. So here still we can get theta 12 is sin inverse of ny, but we don't use that method. We will only use a tan2 function. So that will only give the correct angle. That quantum we provide. Okay. So I know sin 12 is ny, since we are equating that two matrix, and cos 12 is nx. Cos 12 is nx. So theta 12 will be a tan 2 sin 12 cos 12, that is n by nx. So I got theta 12. Still I need to find theta 1 and theta 2. I only have theta 12 means theta 1 plus theta 2. Theta 1 means theta 1 plus theta 2. Theta 1 plus theta 2. I want theta 1 theta 2 because I need to put this in a program. So I want theta. So after getting theta only I can command the my motors to rotate that much. So I want theta 2. So this is a2 c12 plus a1 c1. I can equate that with px. Equate with the px. From there, I can write px c1. Cos theta 1 is equal to px minus a2 c12 divided by a1. I can write cos theta 1. Let me write here. Similarly, I can equate this thing with this py. And from there also, I can write what is S1. Since C theta 1, S theta 1, you can be directly substitute. I know theta. What is theta 1 to I know. So you can directly substitute and find the value. So now you got cos theta and sin theta. Again you can apply the net angle function. So theta 1 will be net angle sin 1. That is theta 1 will be net angle S1 C1. So substitute these values because these are known values. I know Px, I know A1, I know Nx, I know A1, then Py, A2, Ny, A1. I know these values. So substituting this will lead theta 1. Once I know theta 1, I can find, I have theta 1 to alter, so I can find theta 2. So this is the one method to find the inverse kinematic solution. Okay, I'm stopping it here. There is one more method.